Okay, so today we're going to talk a little bit about how to use the t-test function in Excel. And the t-test is a way to compare the averages or means of two different sample groups. So, it was developed back in 1908 by a gentleman named Gossett who worked at the Guinness Brewery in Dublin. And his company had a rule that he couldn't publish, while he was working there. So people, I guess, couldn't trace back to the company itself. But he published under the name Student, and basically today it's known as Student's t-test. So the basic idea is that you have, again, these two groups of data, and from some experiments. So, for example, maybe a control and a treatment group or something like that, and each generates an average. Okay, and we want to understand if the average difference, so here the difference is minus 7.2, is statistically significant. So when you use the word statistically significant, you want to know if this difference, that's seen here, given the variability of the system or the noise, is occurring because of some, let's say, effect of the treatment, or it's by chance alone. So that's what statistical significance really boils down to. Before we start anything, we also want to develop a hypothesis or the question to be answered. And, the null hypothesis, okay, is basically that the two treatment means are equivalent. In other words, the hypothesis mean difference is 0. So, somehow the difference between this one and this one, these two averages, would be 0, around 0 value there. The alternative is that they're actually different, okay? And we're going to always have a planning or threshold value of 0.05, and we'll use this value to compare our p-value to, and we'll talk about that here in a minute. And we're going to use what's called a two-sided test because, when you're hypothesizing the mean value is 0, when you run the actual experiment, you don't necessarily know if control or treatment, the difference in these averages will be above or below 0. So it can go either way. We're going to use a two-value t-test. So, the next thing is, once you've developed your hypothesis, you want to collect your data. And here we have like an example of a, hypothetical data set of some control, let's say, and a treatment. And two things have to happen for the t-test to be, effective. One is that the data is collected independently. In other words, each of these data values doesn't have an influence on the next data value that's collected. They're independently collected, or independent of each other. And also that the data is somewhat normally distributed. So when I say normally distributed, it has that Gaussian shape to it, that bell-shaped curve. At the very least, it should have some degree of symmetry to it, and we'll chat about that in a bit as well. Just a note, the t-test is actually designed for smaller samples than larger ones. So, when you're getting above, 30 samples or something, there's a little different test we'll use, and we'll talk about that in a minute as well. Always calculate the summary statistics, the average, and it's always good to find out because that's what we're going to be working with, and the difference here. Standard deviation, and it's a good indicator of variability, the minimum and the maximum values as well. So just eyeballing this data, you can kind of see that the standard deviations are pretty similar, which would be indicative that the variances are similar. These formulas, by the way, are easily generated using Excel, and you can just see up here how those were generated, so you can just kind of follow along to do it yourself. But the most important thing really is to graph your data. This is always a really, really good idea. So here is a graph of the two columns for the control and treatment, and I just used Excel, where you go to Insert, and you just insert a chart. And here we had our box and whisker plot that we chose. And looking at the data here graphically, you can see from the width of the boxes here that The variability is pretty similar. It's a good indicator of variation, the width of these boxes. And there's also a high degree of symmetry. Okay, so there doesn't seem to be a lot of skewness or anything like that. So, we should be in pretty good shape so far. No big outliers are available either to kind of mess up our values as well. So, looks pretty good so far. So now we've done a preliminary analysis. We're going to calculate our inferential statistics. And the way we do that is we go to Data, and then Data Analysis. And that brings up a menu with a bunch of different options. So we're going to go down to the bottom here. And we're doing the t-test, two-sample assuming equal variances. So this was what I was mentioning before. The variances look very similar, the standard deviations. And if they're unequal, then you want to choose this one. Well, how do you know if they're equal or unequal? Well, you can, kind of do a eyeball analysis, but if you want to do an actual statistical analysis, you can use this f-test for two-sample variances. And I've actually calculated that here in this tab, and you can see how that works as well. The z-test is for two-sample for means. So as I mentioned before, the student's t-test is great for smaller samples, less than 30. But when you get a larger sample and you have a better understanding of what your variance is, your sigma value, or if you know your sigma value, without having to estimate it, the z-test works pretty well. But in most cases, you're going to be doing the two-sample, either equal or unequal variances. The t-test for paired two samples is a little bit different. That's where each data set here, each pair is compared, individually. So an example of that might be you have a sample, and let's say you've split it in half, and you're running one half on, let's say, one instrument and the other half on a different instrument. So same sample running two different, let's say, instruments or treatments, you would calculate the difference of that, that one sample, and then use the average of all those differences. So that's a little bit different, but we're going to go ahead and use this equal variance routine. And we hit OK, and then another window pops up here, and it's asking you where the data is. So variable 1, it's going to be this right here. Notice I've also chosen the label as well. And then the second one is right here. The hypothesized mean difference, we're going to use is 0. So we're assuming that the two groups are going to be tested for equality. And then I check off the label box here, because if you've selected the labels and you don't check this off, it'll give you a non-numeric input error. The alpha or planning value is 0.05, and it's also asking us where we want to put our output. So I'm just going to put it right here in the same place as this other one. And we hit OK. And it's just saying it's going to overwrite what's there. We'll say OK. And there you have it. So this is the summary of the inferential statistics. So let's go over that quickly here. So we have our control and treatment. And again, it's calculated the mean values, as we've done already over here. The variance is calculated. So if you want the standard deviation, you just take the square root of these numbers. The observations, how many are in each column. The pooled variance is basically the weighted average of the two variances here. So that's used in the calculation. Hypothesized mean difference, again, is what we have hypothesized we're looking for. Here, the mean difference of 0. Degrees of freedom is something that's used to determine how much data has been used to estimate the parameters in the test. And this one's important. This is the t-stat. So this is the test statistic. And basically what this reflects, it's the calculation of this difference here, okay, standardized by the noise, okay, the variability of the system itself. So that's important because you're looking at differences within the context of variability. And then you can look at these p-values for either one tail or two tails. So, the one tail, again, is if you're looking for values that are going to be one direction or another. So, if you've got, let's say, a standard number and you're comparing it against, it might be a one-tailed test or something like that. We're going to use the two-tail, and here's the p-value right here. Let me highlight that as well. And here's the critical value for the 0.05 limit. So 2.1 represents, if you look at this t-distribution, which is, all these statistics are based on that t-distribution, it'll tell you what the critical value is on that t-distribution. So if your statistic is above that number, it's going to indicate some kind of statistical significance. And it actually gives you this probability number. So what does this number mean? So basically it says that, if the null hypothesis is true, if these two groups are actually equal, okay, you could see a difference as big as this right here about with a probability of 0.008, or about 0.8% of the time. That tells me that it's pretty darn infrequent. Okay, so it's interpret the critical value. If it's less than 0.05, we would reject the null hypothesis. In other words, we reject the fact that if it's equal, it's equivalent. If this was much larger than 0.08 or 0.05, we would actually fail to reject the null hypothesis. So it's saying that it's pretty infrequent. It could happen by chance alone, but really this difference is probably maybe the result of the treatment as well. You have to be a little bit careful with p-values and planning values. A lot of threshold values are centered around this 0.05 limit, and that limit is decades old. That has been established many, many years ago, and kind of people follow it blindly a little bit today. But it doesn't mean that you have to use 0.05. Some people use 0.02. Some people use 0.01. It all depends on what you're really trying to achieve. And it's also the difference between statistical significance and practical importance. So even though this value is statistically different, or significant I should say, this value may not be important in the research itself. So again, you have to kind of, be a little bit cautious, and you have to understand really your experiment and what you're trying to achieve here. So that's pretty much it for the t-test. I've also included the two variance tests here. So same set of data, and we're looking at the variance. Same principle here. Here's how you calculate that one. So basically this value tells us there is no statistical difference between the two variances. And then the last tab I just kind of want to briefly touch on is the multiple averages. So here we've tested for two averages between these two groups. Multiple averages, you may have something like a control, a treatment 1 and a treatment 2. So the null hypothesis here is that at least one of these means is different than the other ones. Okay, and again, you can graph the data using a box plot to see which ones could be different. And when you run this test, which is the ANOVA single factor, the p-value here is pretty small. Again, it's less than the planning value of 0.05. It says that at least one of the mean values is different than the other ones. So again, to determine which ones are different, the simplest way to really assess that is just looking at the box plots. So there we have the t-test, and then we have an offshoot of the t-test, the multiple averages, and then the two variance test. So it's a pretty powerful little combination of tests that you can use to determine if two groups are somehow equivalent or not. Anyway, I hope this helps, and we'll talk to you again.